Hello, my name is Tawakalt Akintola, and my project is on. I'll be presenting on additive manufacturing of multifunctional polymer-based composite with enhanced mecholuminescence performance. So I go to Florida Agricultural Mechanical University, and my department is in Industrial and Manufacturing Engineering at FAMU-FSU College of Engineering, and I work in the lab, which is a high performance material institute. So the outline of the project will be focusing around the background, which is the introduction and the motivation behind the project, the experimental approach we use, the results and discussion will be focusing around the morphology, the thermal analysis, and the micromechanical results gotten from the experiment, and together with the conclusion. So this project is focused on integrating multifunctional material with additive manufacturing, and this will be able to improve the processing, the synthesis, the mechanical properties, and also have a cost-effective outcome. So introduction on this project will be focusing on how we can easily mix two materials together and get a good processing, and as well as using additive manufacturing to get the final outcome. So the uniqueness of this composite is this material have a good property, and also it's high in mechanical properties. So TL, in case you don't know what TL means, TL is the materials that glow under mechanical force, and this material exhibits light intensity under dark light. So as the force increases, the light emitting from the material increases as well. But the problem now is how we can be able to get a good composite out without matrix mode failure, the delamination mode failure, the fiber mode, and the penetration mode. Some of the researchers have been able to use TL with concrete material to be able to show how light intensity is being exhibited from this material. And technology have been shown that there is increase in the multifunctional use of material in composites from 1912, and you can say gradual process using it for radiology, ultrasonic, and continuously up to 2020. And 2020 target research is focusing on big data, in which we've been able to add to the achievements of this technology, which is a third generation composite. In that way, we can be able to easily diagnose the material, check for the quantification of the damage, which is if the damage is high or if it's low, and easily locate where the damage is and the kind of damage which the composite is exhibiting, and also dictate the damage easily without complete destruction of the material. So moving on to the application of TL. TL has been used for concrete, and also has been used in fiber reinforced polymer composites, whereby TL is mixed within the composite together with the fiber material. And here you can see SAGE in 2001 shows how triboluminescence intensity is being exhibited when there is a force or damage in the material. The highest point of damage shows that that's the point where the material, the damage in the material is being exhibited, which is about 40 intensity units. And also in 2011, Dickens shows that the crack monitoring in short fiber reinforced composite can easily be detected as well. And when you have a short micro crack within the composite, it can easily show multiple emission as the load increases. And this will be able to show the light intensity on the composite without the complete failure of the material. So gradual micro crack within the composite shows emission of light. on the surface. And the matrix cracking identification shows that there is a frequency of TL in the range of 2,691 Hz to about 3,000 Hz, as shown by Josh in 2001 as well. Moving on to our own research, our experimental approach shows we use two materials, which is polystyrene and zinc sulfide manganese. So polystyrene is used as a matrix, and zinc sulfide, which is our TL material, is a powder, which is a multifunctional material that was added to make a composite. So these two materials are being processed using meth extrusion. So this meth extrusion mixed the two materials together, and also we collected our filament. So multiple processing cycle was carried out. So the first process is mixing of the two materials in the extrusion. The second process is breaking up the collected material in the first process, grinding and also re-extruding it for the second process. And the third process is also collecting the second process, the filaments from the second process, breaking it down and mixing it again for the third time, and collecting the material. So these three processes were examined using the SEM and CT scan to show how the TL crystals breaks down from one process to the second process to the third process. Then after that, thermal analysis was carried out to show the thermal stability or thermal degradation that affects the material when processing in the extrusion. And DSA shows the glass transition temperature or the melting temperature for the material, in order for us to know the temperature to set it when printing the filament, when printing with the filament from the printer. And after that, we print out a beam for to be able to use to test for 3-point bending, fracture test, and also later on test we check for the mechanical properties using nano indentation as well as the DMA, which is a dynamic mechanical analysis. So after carrying out this test, the SEM result and the UV light on the first process shows that there's a crystal within the surface of the material in the first process, and when we move on to the second process, the crystal is not as visible as the first process. Same thing happened on the third process. And when we try to check with the SEM, it confirms that the size of the crystal is being reduced from one process to another. And when it goes to the third process, the multi-processing cycle affects the crystal, makes it more evenly dispersed within the composite, but by making it much more smaller than the first and the second process. And with this processing cycle, we were able to achieve a better particle distribution, and also it helps to reduce the sizes of the crystals within the composite. So to further confirm what the third process looks like, a filament was used to reconstruct to show the CT scan image of how the filament looks like. And from the filament, you can see the crystals are evenly distributed, and it's in a very smaller sizes. And from the surface of the image, we can see also the white particles are the crystals, which shows that it's almost of the same sizes, which is about 3 microns, which has been broken down to very smaller sizes, which is achieved at the third process compared to the first and the second process. This shows that the multiple processing of the filament has a positive effect on the dispersion of the crystals within the composite. So to further understand the thermal analysis of the composite, we try to compare polystyrene in the composite. So we did polystyrene also for 3 processing extrusion, same thing as we did for the composite extrusion. So for polystyrene, we can see there is a continuous gradual weight loss in the polystyrene as well as for the composite. So for the composite, it shows there is a slight weight loss in the composite because the initial weight of the TL inclusion in the composite is 40 weight percent, but from the TGA result, it shows that it's about 30 weight percent, which means it's lesser than the weight percentage inputted in the beginning of the process. And also from the DSC confirmed that there is a higher temperature in the composite, which shows here right now that the effect of the TL, which is a zinc sulfide crystal in the composite, shows that it suppresses the polymerization effect on the molecular chain of the whole composite, and also makes it more thermally stable than the polystyrene without the TL inclusion. So it also shows that there is a slight reduction in the glass transition of the polymer. This is due to the degradation through the processing condition, as the material was being processed 3 times. So moving on to the micromechanical properties, these 2 materials, which is the polystyrene and triboluminescent with polystyrene, from the nano indentation result, it shows that there is a gradual decrease in the hardness of the polystyrene, pure polystyrene. So at the 3rd extrusion, it shows that the polystyrene is the hardness is much more lower than the 1st extrusion compared to the composite. Composite at 3rd extrusion shows a higher hardness compared to 2nd and 3rd, and this is because the sudden hardness of the triple is due to the hardness of the zinc sulfide, which was able to, and shows the mixing effect of zinc sulfide particle, which shows that there's a even dispersed particle within the composite, and these are led to the higher sudden increase in the hardness of the triple extrusion for the composite. And when we check to confirm with DMA results, DMA also shows that as the multiple processing cycle increases for pure polystyrene, it becomes more brittle. So from the 1st extrusion shows that as we increase the processing to the 3rd extrusion, it becomes more brittle. So triple extrusion is more brittle than the 1st extrusion for polystyrene. However, for the composite, it shows that it's much ducter than the 3rd one is much ducter than the 1st extrusion, and this is due to the reduction in ductility is due to the increase in the processing cycle of the composite. And for the polystyrene, the processing shortens the mobility of the chain in the polymer, whereby makes it more brittle. And because there is TL inclusion in the composite, it reduces the trend in the ductility compared to polystyrene. So, and after carrying out the thermal analysis, we carried out a 3-point bending test. This 3-point bending test is for us to be able to show the MTS inside with the mechanical test system inside to compare the TL signal emission from 1st, which is single, to double process to triple process. And you can see right here, the uniqueness of the cycle is that as the processing increases, the emission increases without much load. So, however, for the single extrusion, you need much load for it to be able to emit a higher light. And the light is not as high as the triple extrusion, even though you need little load. So the light signal for the third extrusion shows about 3.82, which is 4 times higher than the single extrusion. And this improvement is due to the inclusion of TL and as well as a enhancement of the load transfer of the zinc sulfide crystal particle, which can be able to move from one crystal to another, because it is much more smaller and evenly dispersed compared to the single processing, which has a higher crystal sizes. And this processing effect on the polymer matrix also shortens the polymer chains. So the polymer chain shortens as the material increases in brittleness of the polymer, and this helps the material to be able to release more energy on the crystal, because the composite becomes less brittle, and also helps the energy to be able to transfer within one crystal to another, so thereby exhibiting much light intensity in triple compared to single extrusion process. So in conclusion, we were able to achieve our goal, which is inclusion of the TL emission in the printed composite, and also we're able to understand the processing condition on zinc sulfide particle, which shows it has a much vital role in allowing the Mecholuminescence response on the printed composite. And the next, and we also achieved a better thermally stable material without destroying the zinc sulfide, which is a non-destructive mechanical property after exhibiting multiple extrusion cycle. And the multiple extrusion cycle shows that it has a better improvement in interface between the TL crystals and the polymer, because it helps the energy to be able to transfer from one crystal to another, and also modify the property of the composite. And this helps the signal to be able to for the composite to be able to exhibit higher signal at the third processing compared to the second and the first processing. And in all together, with TL composite material, we can be able to easily detect small damages in a structure without complete total failure of the whole structure. And in order for more information on this project, it's been published. You can go to this website underneath the slide to get more information about the project. So here are the selected references that I used for this slide. And I would like to thank SAMPE organization for giving me the opportunity to be able to present my research and also showcase my talent in material processing. And I would like to thank Dr. Tony Smith, Dr. Don, for their continuous information about this presentation and about the progress in how we can be able to present our research. And I would like to thank my group member, my professor, Dr. Dickens, the corporation that helps us with the CT scan, and as well as the research facilities where I work, and my friends, and my collaborators. And this research is sponsored by NSF and Christ Rise Scholar FAMU. Thank you. Any questions?